Bismillahirrahmanirrahim. Assalamu alaikum viewers. In today's lecture, we are going to move a bit forward in simple regression analysis. We'll basically try to apply Microsoft Excel tools to perform simple regressions. First, we will discuss some basic tools, some formulas, and later on in further lectures, we will discuss an add-in which is basically a data analysis tool with which we can perform regressions. Today we will take a practical question in Microsoft Excel and deal with it in Microsoft Excel, and later we will move to the effects of change in units of measurement, and then we will have an example of transforming some non-linear models to be estimated by ordinary least square. We can transform some models and some cannot be transferred in that order. And in the end, we will be discussing outliers in regression, or the values that can influence the regression statistics, like the parameters, the R-square values, etc. So the first task today is to have a question that you may see in the examination. So you should understand how to attempt the question using basic tools of Microsoft Excel, and we'll advance in some ideas related to simple regression analysis. So in the slide that you will be seeing is basically a model question in the examination. You will consider some data. By data I mean few columns, in this case 2 columns, one containing the variable y and second containing the variable x, which is the independent variable, and we will perform a simple regression analysis. Y is equal to a plus bx, or as you can say alpha plus beta x, or beta naught plus beta 1 into x. So it is basically a straight line, and we fit a straight line through OLS, and we use the tools of Excel today. We'll use them to perform this regression. Later we'll compare the values that we compute manually using Excel, although we are using Excel for the calculations, but I call it a manual procedure because we are yet not using the advanced Microsoft Excel tools or any other software to perform regressions. So we'll first find a simple regression line estimating by using calculations in Microsoft Excel, and then we'll move to compute the F statistic, the T statistic. We'll apply the basic tests, like you have already learnt T test and F test, which are basically the individual variable significance test and the goodness of fit test. We'll use a new formula, that is line ST command, to confirm that we are undergoing a proper manual procedure to compute regressions. But when I say manual procedure, I mean that if you have a paper and pencil and you are computing the regressions or estimating regression lines, how can you perform that? So Microsoft Excel is helpful because usually it is available in your examinations, and you can use the techniques which you will learn today to perform your examinations questions. So later on we will move to the line ST formula and confirm the results or verify the results that we have performed. So we will calculate R square, we will calculate T, we will calculate F with the help of the expressions or formula that are being developed, and then we will use the built-in functions or formulas in Microsoft Excel to verify that we are working correctly, or the results are fine, or they are identical to the what Excel gives in the formula. So today's task is basically an application of simple regression using Microsoft Excel. So in the slide you are seeing a sheet in Microsoft Excel which shows the values of two variables, Q, that is quantity demanded, and price, which is P. Remember that we will treat X as the independent variable and Y as the dependent variable. So Q is basically dependent on price. So you can see that Q is written here instead of the variable Y. We will not change the formulas, so you have no confusion. You think that Q is basically Y and P is basically your X variable, and we will perform Y is equal to A plus BX. So quantity demanded is a linear function of price, although in real life it is normally not a linear function, but for simplicity we assume that it has a linear relationship with the price, and we are also ignoring other variables. As you know, we have tastes, we have prices of other goods, but as we are going to perform simple regression with one independent variable, so we will assume that quantity demanded is a function of price. As you say in the law of demand, other variables are remaining constant. So in the column you are seeing, in the columns, in the third one, you see that we have a product of price and quantity, and then the square of P, and then the square of Q, and then a trend values column, then E and E square. You must be familiar with that. We have already discussed this. So basically today I want to show you how can you perform these procedures through Microsoft Excel formulas. So in the first cell in the third column, C, you see that the first value 25,500 is computed as using the formula equal, all the formulas start with an equal sign, equals A4 times B4. A4 and B4 are basically cell references. So we use cell references. This means that the value of P lies in the cell A4. As you can see, it is 255 in cell A4. And in cell B4, you have the value of P, which is 100. So we need to multiply them to get 25,500. That is easy. Later, you will drag this formula to perform the same calculation for these 10 values. And in the end, you will have the sum using the sum formula, as I have shown in the sum in the first column, which is 2042, sum of values from the cell A4 to A13. This is the way we compute sums. So this is a simple way to manually compute the summations and procedures. In later stages, you will come to know about some tools or add-ins in Microsoft Excel that give you all the results without these calculations. But these calculations are necessary, and they are better because you need some kind of know-how and understanding on what is going behind the formulas and how Excel is going to perform these calculations. So today we are going into the analysis of how Excel basically computes these things. We are going through a manual procedure. In the third column and fourth column and fifth one, you have PQ, P square and Q square. Remember that P is your independent variable, which is X. You can say that it is in place of X. And Q is the dependent variable. Then we have all the values computed. To compute the estimated values of Q, that is the trend values or fitted values, normally if we are performing on paper, we compute the regression line first, which is y is equal to a plus bx, or q is equal to a plus b into price, and then we substitute various values of price into the equation and compute the estimated values of q. But here we can use the formula trend, which is a function or formula in Excel that computes the trend values based on a straight line or simple regression line. So as you can see, I have shown in the slide equals trend. You are seeing that we have given the cell references A4 to A13, but you can observe that we have dollar signs against the alphabets. This is because we don't want these references to change, because when you drag the formulas, Microsoft Excel will change the references. Maybe it changes from A4 to A5, and we don't want that. So to keep these references as A4 to A13, because the values of Q, the dependent variable, lie in the cells A4 to A13. Similarly, the second input here is B4 to B13 with dollar signs against the alphabet, which keeps these constant references. So you have B4 to B13 as the references for the X values. And then you see that we have given another input, that is B4. This is the value of the independent variable for which you are computing the trend value. So the first trend value is computed for the price, which is 100. So B4 contains that value, and we are asking Excel to provide the trend value or fitted value or estimated value of Q based on a regression line. Q is equal to A plus B into P for the value price is equal to 100. So when you get this value, which is basically 256.1439, you will just drag this to the 10th value and you will get all the columns of the trend value. The next column is residuals, and you remember that residuals are basically the difference in the actual value of the dependent variable and the estimated value of the dependent variable. So this is easy. You can use Excel to compute these summations. Note that the sum of E, this is a property of simple regression line, the summation of errors is 0, and you can verify it over here. I suggest that you open your own Microsoft Excel sheet, enter this data. You can stop this video and enter the data, and then move forward with me so that you can yourself perform all these calculations and understand how Microsoft Excel computes these through formulas that we are going to discuss later on. So the last one is square of residuals, E square. As you know, we need the sum of squared residuals for various computations like computing R square, etc. So we have computed the square simply, and the sum is 905.5332. Let me remind you that this sum E square is basically the phenomena that we have tried to minimize. So as we have performed OLS, so we have minimized the sum of squared residual. We got these values by optimizing the sum of E square, by minimizing it. If you remember, we developed some formula, and those formula ensure that we get the values of parameters A and B such that we get the minimum possible sum of E square. So if you change the values of A and B, you will get something greater than 905.5332, which is summation E square. So basically, this is a Microsoft Excel sheet. In the next slide, you see that we have considered P as the variable X and Q as the variable Y, so we don't need to change the usual formula. As you see, B is equal to n times summation of xy minus summation x summation y over n summation x square minus summation x whole square. This was the formula you already used in computing simple regression. So look into the line below the formula. It states equals, which is basically start of an Excel function or formula, equals 10 times C14. This C14 is the Excel reference for the cell in which the sum of xy is contained. So we had computed the summation of xy in the cell C14. If you go back to the previous slide, you can easily see that. Minus B14, you must understand, is the value that is contained in the cell, the sum of which is contained in B14. Similarly, A14, D14, B14, these are all references for the cells in which these required summations, summation x, summation y, etc. are contained. So this gives you a value of minus 0.84737. So minus 0.847 basically is a slope coefficient which states the average rate of change in the variable y, which is q basically, due to 1 unit change in the independent variable, which is your variable price or p. So what we can interpret is that for every 1 unit change in price, there is possible minus 0.847 units change. When we say minus, we mean the change occurs in the opposite direction. So this is the interpretation of the simple slope coefficient. We can compute A by the formula y bar minus bx bar. As you see, A 14 by 10. This is basically summation y over n. 10 is the value of the number of observations, or n, minus K6, which is the value of B. Basically, in the above formula for B, we computed the value of B, which is minus 0.84737, in the cell K6. So we refer to that cell which already contains the value of B and use this value to compute the value of the intercept, or what we call A, which is 340.88. So this is how you can replicate the manual procedure to compute the values of basically the regression coefficients. So when you compute the values of regression coefficients, you can interpret them in usual ways. If you look on the slide, we have used two different formulas of slope and intercept, providing the known values of y and known values of x, which are the references A4 to A13 and B4 to B13. So we basically can confirm the replication of the manual procedure through the slope and intercept formula, and that is easy to understand that these must be identical. They must provide identical results. This is a verification, so you can know whether you are performing the calculations accurately or no. So slope and intercept provide the slope coefficient and the intercept of a simple linear regression line, and we can compare these values. So we can write the regression line as y is equal to 340.8812 minus 0.84737x, which you can see, and we can interpret the value of B, the slope coefficient, as for every 1 unit change in x, on the average, y may change by 0.84737 units in the opposite direction, because the coefficient has a negative value, and that is logical because quantity demanded is inversely related to price. It is an inverse function of price. So if price goes up, quantity demanded should fall. You should have lower values of quantity demanded. So this inverse relationship is confirmed through this regression, although yet we have to perform some tests of significance, whether this value is significant or no, and whether the fit is a good fit or no. So you have got the slope coefficient, which can be interpreted as the change in y, which is basically your quantity demanded here, or q, with respect to 1 unit change in price, which is shown as the variable p, or the variable x in your usual notations for simple regression. As you know, we don't stop by computing the slope coefficient and the intercept and interpreting that. we have to confirm some things. As you remember, we have the individual variable significance test, and then we have the goodness of fit test, for which we need to compute the standard error of estimate and the standard error of B, and then use them to compute the values of T, and we need summation E square as well to perform calculations for the coefficient of determination, which we use in computing the F statistic to know whether the fit is good or no. So in the slide you are seeing that we have computed the standard error of estimate, which is shown as sigma hat E, which is equal to summation E square by n minus k square root of all of it, which gives you 10.63916. How did we manually compute it is clear if you look through the arrow on the right. SQRT, which is basically a function for square root in Microsoft Excel, of H14 by 8. This H14 is the cell that contains the value of summation E square. If you go to the slide which shows the Microsoft Excel sheet with the data, you can see that we have computed the sum of squared residuals in the cell H14. So this formula can, when you enter it, provide you the value of 10.639. Below you see the standard error of B, the usual formula that we have been using, sigma hat E by an expression summation x square minus summation x whole square over n square root. Remember that this summation x square minus summation x whole square over n is basically summation x minus x bar square. So we have transformed it for ease of calculation. And how we can calculate it through Microsoft Excel, replicating the manual procedure, is SQRT, that is square root H14 by 8, which was basically computed above as standard error of estimate, divided by, we have substituted D14 and B14 as the values of summation x square and summation x in the formula, divided by 10, which is n, and this gives you the value of 0.08668. These values will be used in the next slide. Now with these calculations we can perform the individual variable significance test that is usually done with Microsoft Excel tools or other softwares, but to know how it is manually computed, we go through this procedure. You have a null hypothesis which states that B is 0, which means that B may be insignificant in the population, but you have an alternative hypothesis which states that it is non-zero value, that is, it is significant. We test it against an alpha of 0.05 or 5%. That is, you know what is the level of significance, and we use the usual T statistics as B over standard error of B, which already we have computed. So which gives you a value of minus 9.77614, which is computed as K6 by K13. Again, this K6 and K13 are the references of the cells in which we have already computed the value of B and the value of standard error of B. So you can use these references to use the values of B and standard error of B to compute the T statistic, which gives you minus 9.77. Now we compute the value of the table T, which you call it, table T, at alpha by 2. You know that the region of rejection, this is a two-tailed test, lies on both sides. So we look into the value alpha by 2 if we are looking into a table. And at a degree of freedom n minus k, n is the number of observations, k is the number of restrictions imposed, which is equal to the number of parameters in our case as we have defined it. So the value is 2.306. Instead of looking into tables, you can compute it through Microsoft Excel by using the formula equal t dot inv for inverse dot 2t, that is two-tailed, and you give two arguments, that is 0.05 as the level of significance and 8. So this gives you the value of 2.306. Now comparing this value with the value that you already have calculated, that is minus 9.77, you can see that the value is larger than the table value which is provided by Microsoft Excel, and you know that the region of rejection states that if the absolute value of T statistic, ignoring the minus sign, is greater than the table value at the such and such level of significance and degree of freedom, so we reject the null hypothesis and conclude that B is not equal to 0. So we can say in this case our slope coefficient is significant, which means that there are chances, we are 95% confident to state that we are making the correct conclusion that there are chances of the fact that variable x or the variable p in this case significantly affects the variable q or quantity demanded. So through the test of individual variable significance, we can see that the slope coefficient is significant. Now we perform the goodness of fit test. You want to know whether the simple linear equation that you selected is performed well, and we have a good predictive power, and we can safely forecast the values of quantity demanded based on the values of price. So the procedure for F test or the goodness of fit test is that you have a null hypothesis. If you remember, the fit is not good. An alternative hypothesis, the fit is good. Then an alpha, which is 0.05 over here. A test statistic which states that F is based on the value of R square, as you can see in the slide. You can compute R square as 1 minus n into summation E square over n summation y square minus summation y whole square, which gives you 0.9228. We did it in Excel by using the formula on the right side, equals 1 minus 10 times H14, which contains the value of summation E square, divided by 10 into E14. This cell E14 contains the value of summation y square, minus A14 raised to power 2. A14 contains the value of summation y. So basically you can compare it with the formula and see that we have used the cell references which contain the required sums, and the value is 0.9228. So how can we interpret it? The explanatory power of the model is 92.28%. So we multiply it by 100 and say this is the percentage, the ratio of explained variation to total variation, as you had defined the coefficient of determination. So when we use this coefficient of determination to compute the value of the F statistic as given below, we get 95.573. Again, we used the formula M6 by 1 minus M6. We had basically calculated the value of R square in the cell M6, multiplied by 8 by 1. 8 is your degree of freedom because you have 10 observations and you have 2 restrictions, that is 2 parameters in this case. So 10 minus 2 gives you a value of 8, your n minus k or degree of freedom, and k minus 1 is 2 minus 1, which is 1. You can multiply it and get the value of F, which is 95.57. So as you can compute the value of various probability distributions using Microsoft Excel, here also you have a formula f dot inv dot rt. Rt means right-tailed. This is a right-tailed value at 0.05 level of significance. You have 3 arguments in this formula. One is the level of significance, the second is the value of k minus 1, and the third is the value of n minus k. So in the slide you see that we have shown equals f dot inv dot rt with arguments 0.05, 1 and 8. When you enter, you will get the value of 5.3. As you see that the calculated value of f, which is 95 point something 57, is much larger than the value that the table provides us, the value of the probability distribution. So we can reject H naught and conclude that the fit is good. So this is a demonstration of only using Microsoft Excel to perform or replicate the paper procedure or manual procedure that you may perform, and you can use Microsoft Excel's formulas, simple formulas in the examination as well to perform such a model question. So this helps you in how to perform in the examination basically, and how to understand how Microsoft Excel calculates these values. So basically you have concluded that the parameter B is significant and the test is a good fit. Now you can safely move to forecast the values of quantity demanded based on the values of price. Instead of using simple formulas and computing summations and performing the regression through formulas, you can use a command or function or formula line st in Microsoft Excel, which you already used in simple regression. So we use the same example to perform line st to compute various values of regression statistics and diagnostic tests, etc. So in the slide you see that the syntax for line st is known y's, known x's. So we will provide the cell references over here that contain the values of y and the values of x, and then a constant and then stats. So you can just type in, if you have opened Microsoft Excel and you have entered the data, you can select a range of cells. Remember that for line st, the number of columns that you select is equal to the number of parameters. So here you have 2 parameters, A and B. So you will select 2 columns. This is for the results generated by the command line st. So you will select 2 columns, and in all cases you will select 5 rows. When you have selected these, you will enter the formula, press Ctrl and Shift, keep them pressed, and then enter. You will get basic regression statistics shown in the slide as value of B, value of A, standard error of B, R square, F statistic. So the values that you will be getting by entering this formula will be in this order. So if you don't remember them, you have to refer to the slides. So in this case, the values of known y's are contained in the cells A4 to A13, and those of x's, that is your price, are contained in the cells B4 to B13. True and true, you already know that. So press Control Shift and press enter. You will get the values that are shown below. For example, minus 0.84737. This is the value of B, which is exactly identical to the value that we have manually computed. Then you have 340.8812. This is the value of the intercept. As you can see, below the value of B, you have the standard error of B, and standard error of A below the value of A. You have the value of R square as 0.922, that is 92.2%. This is also exactly identical to the value that we computed using simple formulas. Similarly, you have the F statistic as 95.57. 8 is the degree of freedom. You have the regression sum of squares and the residual sum of squares, 905.5332. This residual sum of square is basically your summation E square, which you have already computed by using simple summation formula. So one value is missing over here, that is the T statistic. So that is easy, you know T is B divided by standard error of B. So the first column in the first cell in first column, which gives you the value of B, can be divided to the cell below that, which is the standard error of B, and that will give you the value of T statistic. And you can see that this line ST formula provides identical results to the manual procedure that you can solve a regression equation on paper or using simple formulas in Microsoft Excel. You can use line ST. Remember that I told you in the beginning, we will be using an advanced add-in or tool that is called a data analysis tool. So for the data analysis tool, we'll refer to another lecture, but presently we have used the line ST command to demonstrate that the calculations already done are perfectly and accurately done. Now we'll discuss how the change in the unit of measurement or scale can affect the values of the regression parameters like B and A. So sometimes you need to transform the variables. A linear transformation means that you are multiplying the values by some factor or dividing by some factor. We need this strategy in various circumstances, like for example, if you are recording population, you know that the values are very large. So you can give the population in thousands or millions, that is divide the value of population by 1,000 or 1,000,000. Similarly, if you know the values of GDP or gross domestic product are as well very large, so instead of using very large values, you can simplify by dividing by 1,000,000 and report the GDP in millions, or you may report the GDP in billions if, for example, you are speaking of the United States with a huge large amount of gross domestic product. So in this case, we can divide or multiply the values of the variable or the observations of the variable by a factor, and maybe the coefficients or the regression intercept and slope may change. So we'll see how the change in the unit of measurement may affect the population regression coefficients. So I gave you examples of population and gross domestic product. There are other examples as well. For example, when you report price and you have huge prices, say price of automobile or cars, you may report the price in thousands, or say you have some values that are in millions or billions and you want to report them in millions or billions instead of reporting the complete value. So it is easier. So we divide the variable values by some factor, maybe 1,000, million, billion, and report the statistic. So in this case, there would be some effect on the value of B and the value of A. We'll take an example and perform simple regressions and see how the change in the unit of measurement affects the values of B and A. So if you change the value of the dependent variable, you may observe an effect on both A and B. If you change the value of the independent variable by multiplying or dividing by some factor, you may observe that the slope coefficient only changes. So let's see in the next slide. You are seeing 3 regression tables. Note that in the first table, you have the first column which shows the years from 2008 to 2012, and you have the values of gross domestic product of Pakistan taken in US dollars. So you can see it is large values with many zeros. The source for this is tradingeconomics.com, and the source for labor force, which is in the next column, is indexmundi.com. The source is given above. So you can use other sources as well. For example, you can get such data from World Development Indicators or World Bank websites or World Development Reports, as I told you in the first lecture. So in the first table, you have the raw values of GDP and labor force with many zeros. So it is difficult to understand. Below the table, you have the regression line where we estimated GDP as a function, linear function of labor force, which gives you the value is very large. If we start stating it, minus 1327899076005. So you cannot remember it. Plus 5697.6 into labor force. So this is your B. In the second table on the right, we have just taken the US dollars, the GDP of Pakistan in billion US dollars. So we divided the values of GDP, which were in the first table, by 1 billion, that is 1 and 9 zeros, and we get 143. So 143 billion, 164 billion. So it is very easy to remember the values and understand the values if you express them in the proper unit of measurement. So in this case, we have expressed the GDP in billion US dollars by dividing the actual value of GDP by 1 billion. So 1 billion is the factor, a constant factor, by which we have divided the values of gross domestic product. So the labor force remains the same in this table. So we get the line, the simple regression line, GDP is minus 132.79. See how simple is that compared to the value on the left, plus 0.000, I don't know how many zeros, 5697 into labor force. Again, there must be some adjustment over here. This value 0 point many zeros and some value is difficult to remember, difficult to interpret, difficult to observe and analyze. So we need some adjustment in labor force as well. In the third table, where you have the GDP in billion US dollars as in the second table, but now you have the labor force in millions. This means we have divided the raw values of labor force by 1 million. This is also easy to understand, to analyze, to look into. 48.23, so simple, 50.58. So let's see what happened to the regression coefficients when we divided or multiplied or changed the unit of measurement of the variables, because you most often will encounter such problems or such situations. So in the right side below the table 2, I have given some statements like if we divide the independent variable by a factor, the slope coefficient is multiplied by that factor. As you can see, we have divided labor force by a million. So the coefficient that was computed was 0.00005697. So this has been multiplied by 1 million and you get the value 5.697 in the third table. So note that the value in the third table, minus 132.79 plus 5.697 into labor force, is very easy to understand and interpret. So how to interpret it? Because the values of labor force are in millions. So you'll say a 1 million change in the labor force may increase the gross domestic product by 5.697. That is 5.697 billion, as the values of GDP are taken in billion US dollars. So as you see, if we divide the dependent variable by a factor, the effect is both on the intercept and the slope. They are also divided by the factor. So again, if we divide or multiply the independent variable by a factor, the slope coefficient is multiplied or divided by the factor, an opposite relation, but there is no effect on the intercept. But when we divide or multiply the dependent variable by a factor, the value of the coefficients of both coefficients A and B is divided or multiplied by the same factor. So this is by dividing by 1 million or 1 billion, you can easily conclude that multiplication would produce just opposite results. So why do we use these changes in unit of measurement? If you look at the table 1, 2 and 3, if I ask you to just look at the tables and remember the regression equations, it is very difficult to properly remember regression equation 1 and regression equation 2 and even interpret them. So it is very easy to remember the third regression equation. The values are simple. So if you feel by performing regressions that the regression coefficients are unusual values like 0.0000 something, and you want good values to easily interpret them, so you need to change the unit of measurement accordingly to get the desired effect, to get regression equations that simply can be stated, simply can be interpreted, and simply can be analyzed, as in this case. This is how we use the changes in unit of measurement of various variables to make life easy and to interpret the results easily, to remember the results easily if required. There are two types of transformations that can be done to variables, the independent or dependent variables. Linear transformations, which don't affect the correlation, etc., because you multiply or divide the variables by some factor. As you saw that if we multiply or divide the values of the variables by some factor, we have just change in the decimal place of the regression coefficients. There is no difference in the interpretation. But sometimes we need to perform non-linear transformations that change the structure of variances or correlations. We do that in order to apply the techniques learned in OLS or ordinary least square to models which apparently don't look linear. As you will see in the coming slides that we have various types of models. We can take logs of some variables, we can raise the variables to some power or raise a constant to the power variable power. So we have different types of models basically in econometrics, but we want to use them to simply estimate them by applying ordinary least square. So we need to linearize them or make them somehow look linear so we can apply the ordinary least square technique. In this case, we will be using simple regressions and models, and we look into what is the interpretation of the coefficients in those cases. So as an example, we have taken the Cobb-Douglas production function. If you studied economics, you know that production is a function of factor inputs, that is labor and capital and say human resources and openness. But as you yet have discussed simple regression analysis with one independent variable, so what we'll do, we'll skip all the variables and feel that or assume that the production is a function of only labor. Production means gross domestic, may mean gross domestic product over here. So basically the Cobb-Douglas production form is written as quantity or GDP or production, whatever you call it, is equal to A times labor raised to some power alpha. So we need to estimate this alpha. L stands for labor force, A is an efficiency parameter, and Q or Z or whatever you denote is the production. So this is a production function. So we call it Cobb-Douglas production function. So it doesn't look linear. If I ask you to estimate the value of alpha and you only know how to perform simple regressions, it may be difficult, but it's not difficult. You can transform these into another equation which looks linear, and you can estimate it by OLS and then retransform, if required, the values of parameters to get the actual values of the parameters. So the interpretation would be different as compared to the simple linear regression equation. So in this case, if you look into the slide, you see quantity or the production is equal to A times L raised to power alpha, K raised to power beta. In this case, we have two independent variables L and K, but as we perform only simple regression, we assume that quantity is a function of capital stock only, that is A K raised to power beta. To estimate the value of beta, you can take log on both sides. So log of Q is log of A plus beta times log of K. Now make some substitutions. Let Y be equal to log of Q, alpha equal to log of A, and X be equal to log of K. Then you can write the above equation as Y is equal to alpha plus beta into X. This is the usual simple regression equation. So when you say Y is alpha plus beta X, you can estimate the values of alpha and beta through simple OLS. So the value of beta is basically the same value of beta in the Cobb-Douglas original production function, but the value of alpha is the log of the value of A. In order to get the value of A, you take the antilog of the value alpha and you will get the parameters A and beta, and you can write your production function. So you see we can transform, in this case by taking logs, can be natural log. We can transform functional forms into a functional form that can be easily estimated by ordinary least square, and we can do the job. Some examples of non-linear transformation are in front of you. Remember that non-linear transformation changes the linear relationship between variables, correlations for example. So the first one is standard linear regression, the one you have already discussed and performed. You don't require a transformation. It's a simple equation, y is b naught plus b1 into x, a simple linear equation. And you remember that its interpretation is, the value of b's interpretation is that 1 unit change in x causes b units change in the y, which is the dependent variable. The second model is called exponential or log linear functional form. Note that we have taken log of the variable y, the dependent variable. So the line or the function can be written as, the equation can be written as log of y is equal to b naught plus b1 into x. You can call this log of y as, label it by some variable, maybe y star, and you will have an equation y star is equal to b naught plus b1 into x, which again is simple linear equation and can be estimated by applying OLS. Next is the logarithmic model or linear log model. In this time we have taken the log of x, and the model is when it is transformed to linearize it, to find it, to estimate it, to fit the model through OLS, we have y is equal to b naught plus b1 log of x. As you will see later on, we have different interpretation of this coefficient b1. It is not like the simple linear regression, because it is the coefficient of log of x instead of the coefficient of x. Next is the double log functional form, which where we take the log of y and x both. So the line can be written as log of y is equal to b naught plus b1 into log of x, as you did in the Cobb-Douglas production function. Now carefully look at the table which shows different models discussed already. The first one is linear invariable. So y is equal to a plus bx is a simple linear regression equation in which you have the usual interpretation of the coefficient b. So you say the value change in 1 unit of x may cause on the average b units change in the variable y. So b is called the marginal effect, but you remember as partial derivative, the rate of change of y with respect to the variable x. We call it marginal effect. And you know that elasticity is also computed through a formula. If I state it as delta y over delta x into x over y. So delta y over delta x or dy by dx, which is the derivative basically, or if you have multiple variables, you can say partial derivative of y with respect to x is basically the value of b. So elasticity can be written as b times x over y. In the next model, which is double log form, we have taken log of both x and y as we did in the Cobb-Douglas production function. So see how we interpret the values b and a. B is basically interpreted in percentage terms. When you have logs on both sides, the dependent variable and independent variable, you will interpret as follows. 1% change in the variable x on the average will cause the variable y to change by b%. If b is positive, in the same direction. If b is negative, then the change will occur in the opposite direction. So the only change is that we now interpret, instead of unit terms, we interpret in percentage terms. So a 1% change in the variable x will cause on the average b% change in the variable y. And as you can see, the marginal effect is b times y over x. Basically this is the derivative of y with respect to x. And when we compute elasticity, you have simply b. So a thing that you should note, b, which is the coefficient in a Cobb-Douglas production function, it was beta, or a double log form regression equation that you can estimate, is basically the elasticity. So as we called b a slope coefficient in simple linear regression equation, here we call b as an elasticity coefficient because it is the elasticity basically. So if you remember the Cobb-Douglas production function, beta was the capital elasticity and alpha in the usual Cobb-Douglas production function is the labor elasticity. The third model is level log or linear log form, where we have taken the value of x in logs, natural log of x. So we interpret it as 1% change in x is expected to change y by 100 divided by b units. B over x is the marginal effect and b over y is the elasticity. You have a log level form where we take the log of the dependent variable only. So we interpret it as when x changes by 1 unit, because you didn't have taken the log of x. So when x changes by 1 unit, y will change by approximately b times 100%. The marginal effect is b into x, and the elasticity, when you compute it, would be equal to by. Remember that for computation of elasticities, we use the average values of x and y, the mean values, the arithmetic means of x and y to compute elasticities. So marginal effect of x is basically defined as the partial derivative of y with respect to x. Marginal effect and elasticity may be computed at mean values of x and y. And for interpretation, you can refer to the table we discussed earlier. But one last thing to remember here is that these interpretations are valid only if you have proper regression estimates. That is, we have the property blue, best linear unbiased properties. So when Gauss-Markov assumptions are valid and parameters are significant, then you can interpret the parameters in this way. Sometimes when you record observations or gather data, you have outliers, the values which don't match the usual pattern of the data. They are different from the data. For example, they are very large or very small, or if you plot the observations in a scatter plot, you see that the points lie very far away from the usual points or observations that you can see. Sometimes the outliers cause no harm, and sometimes the outliers are influential. They change or they have an effect on the values of the regression coefficients or the values of the coefficient of determination. So they may affect the predictive power of the model. So in this case, you will be seeing two graphs. In the first one, you have two regression equations. Y is 2.2 plus 0.144x with r square of 0.58. If you look into the circle, you have a point which is quite far away. It is an extreme x value from the usual dots that you can see for the regression equation. Y is minus 3.5 plus 0.47x. See that x, the r square 0.58 changes a lot as 0.91. This second regression is computed without this outlier. So outlier is a point which is far away, which can be of different types. Either you can have a large x value or a large y value, or a point that shows extreme x and y values, or you may have a point that has normal values of x and y but not a normal relation as compared to other points. It is distant from the normal scatter of the dots that provide you with the original observations. So in the diagrams, you see that in both cases you have outliers encircled. So in the circle, you can see that in the first one on the left side, the point has an extreme x value, so we call it an outlier. In the second one, you have another point which is distant, which is far away. It has an extreme x value and unusual y value, which is not basically clustered around the usual channel where the points are moving in a straight line. So we can see that these outliers may or may not affect the values of regression statistic. As in the first example, r square changed from 0.58 to 0.91. So this is a huge change. So we can call this outlier as an influential point. So there are various tests and various ways to know. The basic method to know about outliers is to have a scatter plot. So we plot the observations into a scatter plot and see which are the points which are far away from the normal pattern. You will feel it, as in case of these 2 points in these 2 diagrams. So the next would be to check whether this outlier is influential or no. So an influential outlier is a value that significantly affects the regression, the slope coefficient b or the coefficient of determination. So you need to perform regressions with and without these kind of outliers to know whether these outliers are influential or no. Influential outliers are the outliers that significantly affect some regression statistics like r square and the value of the slope coefficient. So you should be careful about that.